Hello and welcome back. We're diving into another session today, and I want to start with a scenario. Something most of us have probably experienced.
Okay.
You're playing outside, you fall, get a small cut on your knee, you go home, and someone applies that clear liquid hydrogen peroxide on the wound. And immediately you see this white foam bubbling up.
Oh, yes, a lot of fizzing. And it gets a bit warm, too, if you notice closely.
Exactly. We see the same thing in the chemistry lab, mix it with a bit of liver or potato, and it just goes crazy.
It does.
But here's the thing that's always puzzled me. That same bottle of hydrogen peroxide can sit on a shelf for months and nothing happens. No bubbles, no heat. So why does it react with such speed only when it touches blood?
That's the perfect question to start with. See, that reaction hydrogen peroxide breaking down into water and oxygen is always happening, but on the shelf, it's just incredibly slow.
Too slow to even see.
Exactly. It could take years. But the moment it touches blood, there's a biological helper in our cells that grabs those molecules and forces them to react at, well, super speed.
And that helper is what we're here to talk about. Today we're doing a deep dive into enzymes, a critical part of Unit 10, biomolecules.
And for all the students listening, especially those in Class 12 preparing for board exams, this is a topic you really can't skip. The weightage is significant.
But it's more than just marks, right?
Oh, absolutely. If you get the concept clarity here, the reasoning questions become very easy. No need to, rote memorize anything if you just understand the mechanism.
Okay, so let's set the stage. Why should we care so much about enzymes? It's not just about bubbles on a cut, I assume.
Not at all. It's about life itself. I mean, the whole mission of this topic is to understand how we can even exist.
How so?
Our body is basically a huge chemical factory. We're digesting food, building muscle. All these are chemical reactions. Now, in a lab, to speed up a reaction, what do? You heat it up, you boil it.
Right, high temperature.
But our bodies run at 37 degrees Celsius. That's quite mild. Without enzymes, the reactions needed to keep us alive would be too slow.
How slow are we talking?
I mean, if you ate a sandwich for breakfast, without enzymes, it might take 50 years to fully digest it.
We would literally starve to death with a full stomach.
Precisely. So enzymes allow all this chemistry to happen at a speed that supports life, all without needing, furnace temperatures.
Okay, let's break this right down. For a student who finds chemistry a bit intimidating, give us the zero-level explanation. What is an enzyme?
At the simplest possible level, enzymes are specialized proteins. That's what they are chemically. And their only job is to be a biological catalyst. They speed up reactions by lowering what we call the energy barrier.
Energy barrier. Okay, that's a textbook term. I need a picture in my head to remember this during an exam. Can you help us visualize it?
Of course. Let's create a mental image. Imagine you're a hiker. You are the reactant. You're standing at the foot of a huge, steep mountain.
Okay, I'm there, looking up.
And your goal is to get to the other side of that mountain. That's the product. To do that, you have to climb all the way to the top and then down the other side. That climb, that effort, that's the activation energy.
Sounds exhausting and very slow.
It is. Now, an enzyme comes along. The enzyme doesn't give you a piggyback ride. It doesn't make you a better climber. Instead, it's like a giant drilling machine that creates a tunnel straight through the mountain.
And a tunnel. Okay, I see where this is going.
Now, your situation is different. The starting point is the same, the destination is the same, but the path is so much easier. The tunnel has drastically lowered the energy you need to get to the other side.
Wait, I want to clarify something there. The tunnel.
Yeah.
It doesn't change my starting altitude, right? Or my destination's altitude.
That is a brilliant question. And no, it doesn't. That's a very common point of confusion. The enzyme does not change the energy of the reactants or the products. It only provides an easier path. It lowers the activation energy. Nothing else.
So, easier journey, same destination.
Perfectly put.
Now let's zoom in. From the mountain to the molecule. What's really happening, you said they're proteins. How does a protein grill a tunnel?
So if you looked at an enzyme molecule, you'd see this big, folded protein chain. It has a very specific 3D shape. And somewhere on its surface, there's a little pocket or a groove. This is called the active site.
The active site. This sounds like a key word for the exam.
It is the most important keyword. Think of the active site as a lock. And the reactant molecule, which we call the substrate, is the key.
The lock and key model.
You know,
Remember that.
Yes, and it's a good starting point because it explains specificity. Only the right key fits the right lock, right? The enzyme that digests milk sugar, lactase, won't touch any other sugar.
But you said a starting point, so it's not the full story.
It's a bit too rigid. The more modern idea is called the induced fit model. Think of it less like a metal key in a metal lock and more like your hand fitting into a glove.
Okay, a glove.
A glove has the rough shape of a hand, but as you push your hand in, the glove stretches and adjusts to fit you perfectly, doesn't it?
Right, it conforms to my hand.
The enzyme does the same. When the substrate enters the active site, the enzyme changes its shape just slightly to hug it tighter. This squeezing action puts stress on the substrate's bonds, making them easier to break.
So it's an active process. It grabs the molecule and kind of twists it.
Exactly. That twist is what lowers the activation energy. And this temporary combination is called the enzyme-substrate complex, the ES complex.
Okay, before we go on, let's get that anchor definition down. If a student is asked, define enzymes in the boards, what's the perfect answer?
The one that will get you full marks is this. Enzymes are biological catalysts, usually proteins, that speed up metabolic reactions by lowering the activation energy without being consumed in the reaction. They exhibit high substrate specificity.
I want to pause on that phrase, without being consumed. This is where I've seen students trip up. They think the enzyme provides the energy for the reaction.
No, absolutely not. And please never write that in an exam. That's a guaranteed way to lose marks.
So they aren't like fuel?
Not at all. They aren't batteries. They don't get used up. They are more like a workbench. They provide the perfect surface for the work to happen, and then they're free for the next job.
Okay, let's go deeper with another analogy. You've mentioned things like inhibition and cofactors. I think we need a mental movie to tie all that together.
Agreed. Let's build one. I want you, the listener, to close your eyes. Picture a very busy, professional restaurant kitchen.
Okay, got it. Stainless steel everywhere, lots of activity.
In this kitchen, the chef is your enzyme, and each chef has a very specific station.
And the ingredients arriving. They must be the substrates.
Exactly. The raw ingredients are your substrates. Let's say the chef is a pizza specialist. The dough and sauce are his substrates. They arrive at his station.
Which is the active site.
Correct. The chef works on them. This is the ES complex forming.
Yeah.
Then out comes a finished pizza. That's the product.
And the chef himself
Wipes his hands, ready for the next order. He didn't become part of the pizza. He is reusable. That's why a tiny amount of enzyme can process a huge amount of substrate. One chef, hundreds of pizzas a night.
But sometimes the chef needs tools, right? He can't just use his bare hands for everything.
Excellent point. To chop onions, he needs a knife. In biology, that knife is a cofactor.
The cofactor?
Yes. Many enzymes are useless on their own. They need a non-protein helper, like a metal ion or a vitamin molecule, to work. Without the knife, the chef is just standing there. The enzyme is inactive.
So that's why vitamins are so important. They often act as these cofactors.
Precisely. They are the tools for the chefs.
Okay, let's add some drama to our kitchen. What if someone wants to stop the chef? This brings us to inhibition.
Right. Imagine a rival chef from another restaurant walks in, and he looks almost exactly like the pizza dough. He just goes and stands at the chef's station.
Blocking it. So the real dough can't get there.
Exactly. The station, the active site, is occupied. This is called competitive inhibition. The inhibitor molecule competes for the active site because it has a similar shape.
Is there a way to fix this? Could we just flood the kitchen with more real dough?
Yes. If you throw enough real dough at the station, you'll eventually push the imposter out of the way. So competitive inhibition can be reversed by increasing the substrate concentration.
Okay, but what if the rival is sneakier?
Now you're thinking about non-competitive inhibition. What if the rival doesn't go to the chef's station? Instead, he goes behind the chef and maybe ties the chef's hand behind his back.
Oh, so he's not blocking the active site directly.
Not at all. But by binding to another part of the enzyme, he has changed the chef's shape. The active site is now distorted. The chef can't work properly anymore.
And in this case, adding more dough won't help at all.
It won't make a difference. The chef is tied up. That's a crucial distinction for the exams. Competitive is fighting for the same spot. Non-competitive is breaking the machine from somewhere else.
That clears it up so well. Okay, let's step out of the kitchen. Let's talk about real-world factors, like heat. You said enzymes work at body temperature. But in chemistry, we learned heat makes reactions faster.
It does, but only up to a point. Let's go back to our very first example with the hydrogen peroxide. You take that piece of liver with the catalase enzyme, and you boil it for 10 minutes, then you cool it down and add the peroxide. What do you think happens?
Based on what you're saying, probably nothing.
Exactly. Silence, no bubbles.
Why, though? The protein is still there, isn't it?
Yes, but this is denaturation, and please, the wording here is very important for marks. When you overheat an enzyme, you are not breaking the amino acid chain. The peptide bonds are intact.
So the string of bees is still there.
The string is there. But remember that complex, folded 3D shape, the chef station? The heat makes the molecule vibrate so much that it just unfolds. It becomes a messy, useless thread.
The lock is melted.
Perfect analogy. The active site loses its shape. And in biology, shape is everything. No shape, no function. That's why a very high fever is so dangerous. It's literally cooking your enzymes.
Okay, one last factor, concentration. If the chef is reusable, does adding more and more ingredients always make things faster? Is there a limit?
There is always a limit. We call it saturation. Let's go back to the kitchen one last time.
Yeah.
You have 100 chefs. You send in 10 pizza orders. They're done instantly.
50 orders, still very fast.
100 orders. They're all busy, but working at top speed. Now, what if you send in 1,000 orders at once?
It won't get any faster. Still only have 100 chefs.
Exactly. All the chefs are occupied. They are working at their maximum speed, what we call Vmax. Adding more substrate, more ingredients won't help. The system is saturated.
So the reaction rate graph goes up and then just flattens out.
It hits a plateau. At that point, the enzyme concentration is the limiting factor.
Okay, this is so clear. Now let's connect this to technology. How do we use this knowledge in the real world?
A fantastic everyday example is lactose intolerance. Milk has a sugar called lactose. To digest it, our bodies need an enzyme called lactase.
But many adults lose the ability to make it.
Correct. So when they drink milk, the lactose isn't broken down and it causes, well, problems. So what have we done? Biotechnology companies now produce the lactase enzyme and sell it as a pill.
So you're literally just swallowing the missing chef.
That's exactly what you're doing. You take the pill with milk, the enzyme goes to work in your stomach, and it breaks down the lactose for you. A direct, real-life application of enzyme specificity.
That's amazing. It's not just theory. It's a product you can buy.
Absolutely.
We've covered so much ground. Let's try and summarize this for a student doing a last-minute revision. What are the absolute must-know points?
Okay, let's do some rapid-fire clarity checks. First, the core idea. Enzymes are biological catalysts. They lower activation energy. They are not used up in the reaction.
Got it. And the mechanism.
It works through the active site. Remember, lock and key for specificity, but think induced fit, the glove for how it actually works.
And the kitchen analogy helps with.
Everything else. The chef is the enzyme. Cofactors are the tools. Competitive inhibition is a look-alike blocking the chef's station. Non-competitive is someone tying the chef's hands.
And finally, the factors that affect them.
Temperature. Too much heat causes denaturation. Remember, this unfolds the 3D tertiary structure. It does not break the peptide bonds.
Crucial distinction. And concentration.
The reaction rate increases until it hits saturation, or Vmax, where all the enzyme active sites are occupied.
That's a fantastic summary. Before we sign off, I want to leave our listeners with one final thought. We've talked so much about how specific these enzymes are. One enzyme for one job.
It's actually quite profound when you think about it. Your body contains thousands and thousands of different enzymes, each one coded by a specific gene, each one folded into a unique shape to do one and only one job. What happens if just one of them is missing, or is made with the wrong shape because of a genetic mutation?
The whole assembly line for that one product just stops.
It stops, and that is the basis of many genetic diseases, a single missing enzyme in a long chain of reactions. It shows you just how incredibly intricate and also how fragile this chemistry of life really is. We are functioning only because millions of these tiny molecular chefs are doing their job perfectly every single second.
A powerful thought to end on. Next time you eat something, just take a moment to appreciate all that invisible work. That's all the time we have for our deep dive on enzymes.
Study well, keep your concepts clear, and all the very best for your exams.
We'll see you in the next one.